On March 9th, 2023, Russia made international headlines again as it deployed a barrage of Kinzhal hypersonic missiles during its invasion of Ukraine. The attack killed at least 9 people and caused damage to major energy and military installations as Ukrainian missile defense systems failed to track and intercept the barrage. A hypersonic object is anything which is traveling in excess of Mach 5 or greater than around 4,000 miles per hour. Virtually undetectable by conventional missile defense and satellite tracking systems due to their speed, hypersonic missiles are truly the next leap in warfare, on par with the development of the nuclear bomb in 1945. But what technology allows modern vehicles to attain such blistering speeds? Let's discuss the engineering behind hypersonic propulsion. Modern surface and air-launched hypersonic missiles will often consist of two propulsion systems, a solid rocket booster and a supersonic ramjet, or a scramjet. In order to understand why hypersonic missiles need two different propulsion methods, we need to discuss the performance regimes of various propulsion systems. And for that, we can use the propulsion performance plot, and here we can visualize the effectiveness of different propulsion methods over a range of speeds or Mach numbers. We can see that at low speeds, turbofan engines similar to those found on passenger jets are extremely effective, but as vehicle speed increases, new propulsion methods are needed. At speeds excess of Mach 2 or 2 times the speed of sound, a ramjet engine is optimal. And furthermore, as we approach the hypersonic regime, which is again Mach 5 or greater, even the ramjet engine needs a modification. And thus we have the scramjet. A scramjet engine is the key to hypersonic propulsion because it is able to intake, compress, and combust high-speed air without the need for any moving parts inside. However, the scramjet has one major drawback: it cannot be used at low speeds. Therefore, the hypersonic vehicles need a booster stage in order to bring them up to the effective speed that the scramjet requires. And for that, we use the solid rocket booster. A solid rocket booster, aka solid rocket motor, or SRM, is a chemical propulsion system in which solid propellants are ignited, burned, and then exhausted out of a nozzle to provide thrust to the vehicle. There are entire engineering disciplines focused on the design and optimization of SRMs, and we will not delve into the details of them in this video, but it is important to understand that SRMs are the key to increasing the speed of hypersonic vehicles up to the Mach 4 to 5 regime. And this is where the scramjet engine is able to take over and propel the vehicle forward. So now let's discuss the engineering and physics of the scramjet engine. With only 3 major components, the inlet, the combustion chamber, and the exhaust, the scramjet seems deceptively simple in comparison to a traditional turbofan found on a passenger aircraft. So once a vehicle has reached approximately Mach 5, the SRM is jettisoned and the inlet to the scramjet is opened. Air enters at blistering speeds and collides with the walls of the inlet, and like a pinball, the air molecules bounce between the inner walls of the inlet and create a shock train. Through the inlet shock train, air is compressed and prepared for combustion within the combustion chamber. The design of a scramjet inlet is a very tricky balancing act. Without the moving components present in a turbofan, the compression of the air is entirely dependent on the geometry of the inlet. Too little compression and the combustion will fail. Too much compression and the vehicle structure may fail under the pressure. The next stage in the scramjet cycle is the combustion chamber. Fuel is sprayed into the compressed high-speed air and an igniter starts the combustion process. The scramjet combustion chamber has its own unique challenges. Mixing fuel with and igniting air moving upwards of 3,500 miles per hour is no simple task, and then keeping the flame lit while the vehicle moves at speeds up to 10,000 miles per hour is even more challenging. A good metaphor to describe this challenge is keeping a match lit in a hurricane. Once the air and fuel mixture is ignited, the gases are expelled out of the diverging exhaust, similarly to a traditional turbojet. The acceleration of the gases out of the exhaust creates thrust to propel the vehicle forward. And there you have it, a simplified explanation of hypersonic propulsion. I'll see you in the next one. Shaktiman out.